Good morning, ladies and gentlemen. Welcome to this special lecture by Professor Steve Chu. We are very pleased to have Steve Chu to visit Taiwan for, I don't know, fourth time, fifth time, many times. So he doesn't need very much introduction, but I still briefly introduce his background. Steve received his undergraduate degree from University of Rochester in physics and mathematics, and then PhD degree from UC Berkeley in physics. That was in 1976, I believe, in the PhD. And then he received the Nobel Prize in physics in 1997 for his work on laser cooling and trapping of atoms. It's a very important contribution. And then he served as the Secretary of Energy under the Obama administration, the first term of the Obama administration. And during that time, he started an agency called 𝑅𝐸 Advanced Research Project Agency. Under that, he started many advanced research related to energy. I was also involved in the early efforts. Many of my work was funded by 𝑅𝐸 at that time, and that became our current focus of energy research in Academia Sinica. Today, we're very pleased and very honored to have Dr. Chu to give us this special lecture. Let's welcome Dr. Chu.
All right, sorry for the delay, but let's hope it works. And thank you for the kind introduction. So let me just begin. First, let me tell you that the climate is changing, and that the first UN goal of 1.5 degrees centigrade, keeping below 1.5 increase since the beginning of the Industrial Revolution, has already been passed. We're now at about 1.6 degrees centigrade, and as you see, climbing rapidly. But this is just the tip of what you can expect, what damage we've already done. The reason is the oceans are very cold. The mixing of the surface temperature with the bottom of the ocean is very slow, maybe a 100-year time constant. That means the heat coming in to the Earth, less of it escapes due to the greenhouse gas effect, and 90% of the heat is going into the ocean. So the weather, which is determined by the surface temperature of land and ocean, is being moderated considerably. So what you see in weather in the last decade or two is nothing compared to what we really did. This is not appreciated, especially in the United States. It should be appreciated that people say, well, let's wait a little while to make sure and whether this weather is just a fluctuation or not. And so you have to actually understand that these things are now being measured over the last decade or two. Where are we now? We're at this path. This is 2022. We're emitting 53.9 gigatons of carbon dioxide equivalent. Equivalent means there are other greenhouse gases like methane, N2O, that also contribute to greenhouse gas effects. And right now we're worse than the current policy pledges made in meetings like the IPCC, but those pledges are predicting through climate models that we will end up about 3 degrees centigrade above the Industrial Revolution. In order to get to 2 degrees, 1.5 we've already passed, even to get to 2 degrees, the total greenhouse gas emissions in the world has to go to 0. And so you've heard this expression, net zero. Another concern, a particular concern of mine, is that the social order of the world might be at risk. There are about 15 million refugees, most of them coming from poorer countries, for example, into Europe, the United States. That has profoundly changed the politics of these countries. There's a hard swing to conservative politicians, and their running platform is, we don't want more immigrants. In fact, we want to send a lot of them back home. And so if you think about 15 million or 10 million changing world politics, and if you believe the World Bank estimate of 200 million by 2050, we're going to have a really serious situation. When I was Secretary of Energy, the ministers in India, I met with them, and they were terrified. This is 2009 to 2013. That very poor people from Bangladesh, with rising sea levels and storms, would swarm into India. It's poor Muslims going into a mostly non-Muslim, mostly Hindu country. And they said, what do we do? Do we shoot them at the border? And they didn't know what to do. Hopefully they don't shoot them at the border. But this is a real concern. Okay, so what does it mean to have total greenhouse gas emissions? Again, from the IPCC summary for policymakers, you see that things that you know about, for example, decarbonizing electricity production, is only about a quarter of the world production of greenhouse gases. A very significant thing is if you include agriculture, forestry, land use, food waste, and other things, it's about 1/4 of greenhouse gas emissions. But greenhouse gas emissions also comes from the production of many of the materials we use today: concrete, plastics, steel, cements, textiles. And as I said, the food production is a huge unsolved problem. We don't have a technical path yet to get rid of greenhouse gas emissions from food. This is going to be partially a history lesson. I'm a big advocate of the importance of studying history, and so I remind you of this cartoon I love, where this elderly, wise person says, those who don't study history are doomed to repeat it, yet those who do study history are doomed to stand by helplessly while everyone else repeats it. I study history, and I'm doomed to stand by helplessly. So, a little good news. The little good news is that renewable energy, particularly solar, photovoltaic, and onshore wind, are coming down very rapidly. This is only over a 9-year period. If you look over a 50-year period, solar photovoltaic decreased to maybe 2% of its costs in the middle of the 1970s, 1980. It's only 2%. Imagine a car that costs only 2% of what it cost in 1980. It's much cheaper than your motor scooters. So this is all good. Nuclear power, unfortunately, has gone the other way. It hasn't increased. And so that's where we are. And I would say we need a fourth industrial revolution. It's got to be powered by carbon-free. The first industrial revolution is the invention and improvement of the steam engine, the use of fossil fuel, first coal and then oil and gas. But don't be so confident that since wind and solar are now comparable in price to coal and natural gas, that the war has been won. I want to convince you that all the other supporting factors to support renewable energy, like backup generation capacity, energy storage, enhanced transmission and distribution, those things cost a lot of money, and they are in part of the real cost of renewable energy. And so renewable energy has to be roughly 2 times cheaper than natural gas in order to be really economically competitive. And low-cost energy storage is also crucial. There was a study made by some veterans of ARPA-E, and they said in order to be competitive with natural gas in the United States, where natural gas is very inexpensive, it's only $3 per million BTU. We don't subsidize energy in the United States. I think Taiwan does, so I can't compare natural gas in that. But they said that the energy storage costs had to be at least 10 times lower than current technology. And so that looked pretty hopeless, but then there's something else that happened. And what else happened was that California is now 70% electricity generation is carbon-free. We're going to probably go to 80-90% within a decade. But when you get that much renewable energy, and it's increasing solar, we also have wind, we have hydro, we have geothermal, but the predominant increase is now in solar. And then you see in this time scale, over the course of one day, this is during a summer day, in the noontime where the sun is at its peak, there's an excess of electricity being generated in California. The excess of electricity means they're giving it away for free. In fact, they're giving you money to take it. By the way, this will not happen in Taiwan. You don't have enough solar. And since electricity is free, it means that you can have expensive batteries. You can charge the batteries for free energy. And those batteries are needed because when you go to 4, 5, 6, 7 o'clock at night, where in the summer air conditioning really is needed, this increase in energy is tremendous. We're talking about 14 gigawatts over a period of just 2 hours. So if you want batteries to shift the load from the peak noontime to the peak usage time, these batteries have to supply roughly 14 gigawatts in 2 hours, 7 gigawatts per hour. That's a lot of battery storage. This breaks down in detail what we are seeing now in California. May of 2024, this yellow thing is solar energy. And at noontime, you see that all of a sudden we have too much electricity. So we begin to export it to other states. They'll take it for free. The price is right. But what that meant is you can actually use very expensive batteries because you use this battery, you get nearly free or better than free electricity. And then when the price goes into 4, 5, 6 o'clock, if you have what we call real-time pricing, that's what does it really cost the utility company to generate the electricity, they're willing to pay 10, 50 times more, at least 10 times more. And so a very expensive battery, you say, okay, we just shift the load and at 5 o'clock we give you electricity. So the economics change because of real-time pricing. But real-time pricing, it does not go into the consumer level because most people are not going to pay attention to the cost of electricity and how much it really costs to generate. And so if we had real-time pricing for consumers, the consumers would just see their electricity bill go up. So before real-time pricing can hit the consumers, all the appliances, the clothes washers, the washing machines, the dishwashers, even air conditioning has to be automated so that that consumer can program the thing. If electricity costs 10 or 20 times more than it usually costs, you turn it off, okay? If you don't have that automation, all they see is a higher bill and they scream to their mayors and representatives, and so it's no good. Okay, but that will occur, but it has to be written into the appliance standards of the future before it's going to occur. The makers of refrigerators will not do this for free unless they're required. And they'll never do it for free anyway. They just add it to the cost of the refrigerator, but it's a small cost. Energy storage is crucial. And this is my favorite form of energy storage. When the wind blows and the sun shines, you do use the electricity to do something you would have needed to do anyway. For example, in irrigation, you want to pump water from underground to this water tower, so the wind blows. The energy consumptive part is done. You want the water, you open up a valve. California uses about 10 to 20% of all its electricity to move water. So this is a significant thing. But moving water from the bottom of the dam to the top of the dam, if it's 100-foot altitude, can be very, very efficient. It's just gravity. You take a mass, it takes a lot of work to move it up, and then you let it come down. You can say, that doesn't sound very efficient, but indeed it is. With modern turbines, you can lift the water up and then let it come down a day later, a month later, whatever, and the round-trip efficiency is 75% efficient. That is not good compared to lithium-ion batteries for computers and cars, but it is comparable to mass storage flow batteries. Flow batteries are roughly 80% efficient. So this is a good technology. It's been around for over 50 years, And 95% of all stored electrical energy is in the form of pumped storage. If anyone has a dam already existing, you fit it for pumped storage, lowest cost. Let's talk about conventional batteries. What matters in conventional batteries is how much energy there is per unit weight and how much energy there is per unit volume. For cell phones, the energy per unit volume is extremely important because everybody wants a longer lasting, more powerful phone, but it has to be slender. For cars, both are important. The battery can't take up much volume, but it also can't lug around 1,200 to 1,400 pounds, which the modern 350 mile range cars do. So what to expect from this? This circle is a Tesla battery, and I think in maybe 10 years, the energy density will increase significantly from roughly 200, 250 kilowatt hours per battery cell to maybe 450, 500. I'm on the board of a battery company that was founded in Stanford, and we're shipping samples out that are 450 watt hours. There's an even better battery we ship out, but it costs too much to make. It's only appropriate for drones. Drones you use once or twice, maybe 10 times, they get shut down. But for automobiles, you want a battery that lasts 15 years. Okay, so these are batteries now being shipped to customers as samples. The wonderful thing about batteries is there's been a remarkable improvement in lowering the cost of production. This is called a learning curve. For most technologies, virtually all technologies, if you say you have a certain amount you've manufactured, you double it. The price goes down by a certain fraction. I'll make up a number, 10%. Double it again, it goes down by another 10%, double again. So what does that mean? 10%, 10%, 10%. That's on a logarithm, that's a straight line. So it's decreasing exponentially as you're increasing the production exponentially. So on a log-log graph, you get a straight line learning curve. It was true of the Model T, it's true of batteries, it's true of solar, it's true of virtually everything. There's no deep physical principle for that, it just happens to be. The slope of the learning curve could be very different. Very different for semiconductor chips than it is for other things. In any case, we are the benefit of this learning curve. In 2000, the batteries before huge mass production, they were $2,000 a kilowatt hour. $2,000 a kilowatt hour, pay attention to the numbers. In order to have utility scale storage, it has to be $10 or $20 a kilowatt hour. Okay? But in 2020, it's roughly $100 a kilowatt hour for the battery cell, and by 2030, maybe $50 a kilowatt hour for the cell. If you consider the whole package that goes in the car, already the OEMs are saying maybe $100 in the next couple of years. So the price of batteries will go down twofold. Very good news, but then the question is, what breaks the learning curve? Well, you run out of leg room for a variety of reasons in semiconductor chips. Your 2 nanometer design rule, TSMC, another 1 nanometer and you're end of the line. You're just 5 atoms thick. And so you break the Moore's law learning curve by doing other clever architecture things. In batteries, what might break the learning curve is the resources of raw materials, cobalt, nickel, and lithium. Already, cobalt and nickel are increasing in price, so much so that car manufacturers are beginning to use iron phosphate. It's a compromise. Iron phosphate doesn't have as high energy density, so you have to make a bigger, heavier battery or less range. What about lithium? Well, curious thing about lithium is if you look at the stuff you find in the Earth's crust, the most abundant stuff, oxygen, silicon, iron is over here. Whereas lithium is down here. This is 3 orders of magnitude from here to here, so it's not as abundant, for example, as iron by a factor of 100 or more, but is as common as nitrogen or chlorine, which are not considered rare. And so The question is, if you can mine this in an economically viable way, we'll have plenty of lithium. You don't need that much lithium in, surprisingly, in EVs. So people have begun to look at how you can mine lithium from salty water. Chung Liu was a graduate student at Stanford with 𝐿 and now then became a postdoc in my group. And together we, largely Chung Liu takes, I give much of the credit to her, has figured out a way of taking lithium ions. This is a cartoon, the red and white guys are water. These are cartoons of lithium plus the so-called hydration shell. It's a shell of water around these guys. And she found that if you put lithium into iron phosphate, a cheap battery material, you can preferentially put in lithium and exclude the other ions, and then you reverse the charge and out comes preferential lithium. She's improved this since becoming assistant professor at the University of Chicago, and she can start with a ratio of lithium to sodium in seawater of 1 in 20,000 to get to 8-to-1 lithium to sodium in one fell swoop. But it's a two-dimensional effect, and it's very clear to both Chong and myself that you don't want this. You want a membrane that passes it through and gets it, it doesn't have to be that selective. It can be 5-fold selective. Why? Because you go from one side to the other side, you get 5 times more lithium than sodium. You pass it through another membrane, you get another 5 times, and then again, you just multiply it up. And so that's the goal. There are already startup companies trying to develop methods of getting lithium out of salty water. Where you drill in the ground, you get very salty water, and then you pump the rest of the water back in. So it's very non-polluting. Already in California, there's a startup company not using her technology, but another technology. So we think there will be enough lithium for a couple hundred years. But remember I told you that nickel and cobalt is too expensive, you've gone to iron phosphate, but there's a long dream of over 2 decades. People have realized if you use a metal anode of lithium instead of lithium in carbon, which is today's technology, moving to lithium in silicon nanoparticles, which is now being deployed and beginning to be sold, at least at sample levels, that increases the energy density of the anode 8-fold. If you go to lithium metal, you increase your 12-fold higher energy density. But sulfur is really abundant. It's super cheap. We have mountains of sulfur everywhere. As long as we use fossil fuel, we have to desulfurize those fuels, and so it's piling up everywhere. The oil companies, it's coming out of their ears of sulfur. And they put, the tar that you put in blacktop, it's 40% sulfur. They gotta hide it, they gotta use it for something. And so if you can use sulfur as a battery, it will become very, very high energy density if you solve a few other problems. What's the problem with the metal anode? Suppose you have a little bump. It's lithium metal and there's a little irregularity and there's a little bump. Okay, imagine an electric field driving the lithium from the cathode back onto the anode, and it sees this little bump. Well, in physicists know, as if you take elementary physics, you'll know that this is a higher electric field, and so this little bump then attracts more lithium to the bump. The bump grows and grows and grows, and it forms dendrites. Those dendrites grow and short out the battery. And so lithium metal is very dangerous because you can get a very quick sudden death short. The idea of stopping the dendrites from forming, there are several approaches. One approach is to use a better electrolyte that has a stronger passivating layer. Another favored is to use the solid oxide electrolytes that's stiffer, but the trouble is those electrolytes, solid state electrolytes, don't work well at room temperature and certainly don't work very well at cold temperatures. So another approach taken by me and also in collaboration with 𝐿𝐴 is in addition to the passivating layer, if you can introduce another layer, very, very thin, that passes lithium quite easily, it has a high tensile strength. This high tensile strength can actually be grown on the anode, and when you charge the battery, the lithium goes through. But no bumps can occur because they don't have the strength to poke through this material. And so we're doing experiments in hexagonal boron nitride. It's multi-layer, it's not single-layer stuff. And what we found in a trial a couple of years ago is, for the first time, you can get a lithium metal anode battery to be absolutely stable over 300 discharges, and then it dies. This is a big breakthrough because in all other attempts, the battery begins to degrade immediately. Now, why did it die? It's because of known electrolyte chemistry between the metal, the sulfur, and the electrolyte. So then there are electrolytes that don't do this. So why haven't we published this? This is 3 years old. It's because our source of hexagonal boron disappeared. Around the world, it disappeared. And so I'm now resigned to try to figure out, we want to make it a large volume. Large volume means battery volume, cheaply. Don't know if it's possible, but I'll give myself 50-50 odds that we can figure that out. And if that works, we have a lithium metal battery. Other forms of energy storage is you have forms of energy and you convert it directly into chemical form. So that's chemical storage like a battery, but without the overhead of all the other stuff of a battery. And as every academic knows, low overhead is good. The source of hydrogen today is you take natural gas, mostly methane gas, and in this process called steam reforming, you can convert it ultimately into hydrogen and CO2, and you just vent the CO2. So it's no better than burning natural gas in terms of climate. It's a little better if you're in a city, because when you burn hydrogen or use hydrogen in a fuel cell, it's much less polluting, but in terms of climate, no better. There's a form called blue hydrogen. You have the same process, but you capture the carbon dioxide and you sequester. It's typically underground. That sounds pretty good, but there have two obstacles. You capture about 92% of the carbon dioxide. The others you can't. The carbon capture is expensive, and the mere fact that you're drilling for natural gas in oil and gas fields and poking holes in the ground disturbs the ground, and it leaks out, not in the pipe where you want it, but it just leaks out, 2 or 3%. So when all said and done, it's cleaner, but it is not clean. You've got maybe 10-15% CO2 coming out. The cleanest, of course, is if you make hydrogen using completely clean sources of energy, solar, wind, nuclear, if it's carbon-free also. But these are the prices. And so the so-called green hydrogen today is not economically viable. Nevertheless, if we had hydrogen, we can use hydrogen to reduce iron ore to make steel. And so we use coke from coal to do the reduction, and we can decarbonize steel. You can begin to decarbonize many of the processes to make plastics, chemicals, fertilizer, and it can be a precursor to aviation fuel. So hydrogen will play an important role. We don't know how to make hydrogen without precious metals, so it's a non-starter at scale. And finally, hydrogen is extremely leaky. These molecules go through lots of stuff. They make steel, most steels brittle. You can't use it in natural gas pipelines, it would leak out. And worst of all, we can't remotely detect hydrogen optically. There is no optical signature. It's a symmetric dipole. And but we can do, there are two options. We can miniaturize mass spectroscopy. What mass spectroscopy is, you take something, you ionize it in high vacuum, you energetically put it in a magnetic field, and different masses bend differently. So that's how we detect helium. That's how we can detect hydrogen. It sounds like a big deal, but it can be made as big as my fist. And you can put it on a drone. There's another approach. You can chemically have hydrogen attached to something, and it gives a chemical signature, and then you can chase the hydrogen off and so you can use it again. So those are possibilities, but not commercially viable now, but there's no real technical problem. Another thing that's nice is fuel cells are getting more efficient, and solid oxide fuel cells that operate at high temperature, not appropriate for electric vehicles, but fine at stationary applications. These fuel cells are now beginning to be 70% efficient at converting hydrogen into electricity or electricity into hydrogen. So you can send electricity over a wire, you can produce hydrogen at the site, the oil refinery or the steel plant, as you need it, and that's a big deal. Ravi Prasher was someone I recruited to join me at the Department of Energy as part of ARPA-E. He's now the CTO of Bloom Energy. He used to be Associate Lab Director of Lawrence Berkeley Lab and was offered over $1 million salary to join this company. So, and he said, he kind of said this sheepishly to me, but it says, but this is the only way I see we can use hydrogen. So it is a good thing. New kid on the block is actually something where you can possibly mine hydrogen. Deep underground, you can have rocks rich in iron ores or magnesium, and the chemical state of these ores, if it's an Fe2+, you add water and the heat, you don't have to add the heat, it's hot already, and you change the oxidation state of the iron and out pops hydrogen. And so this has caused a lot of excitement. All the oil and gas companies are looking hard at this, and they're now springing up, those startup companies, not surprisingly from former members of oil and gas companies, to see if you can mine hydrogen. The estimate of how much it costs is over the map. Since it hasn't happened yet, you can guess anything, but it could be less than $1 a kilogram. You solve a problem. You get the hydrogen where you find it, not where you want it. And so the prospect is you take hydrogen and you turn it at the site, at the geological site, into ammonia, into green methanol, into something else. And eventually, if you can figure out how to detect hydrogen, then you can do it in pipelines. So that is another possibility. Material resources, again, just like the lithium thing, it really, what I do is I go back and look at all the fundamentals of what the problems and challenges are. And one of the fundamentals is, where does this stuff come from? What stuff? The stuff we use in the earth. And most of what we use in the earth are two things. It's concrete, and also the ingredients that make asphalt and cement. And on the other side is oil, coal, natural gas, and steel. This is an order of magnitude per division, and so aluminum is 2 orders of magnitude down from steel. This stuff is plastics made from fossil fuel. So this is the most abundant stuff we have, and by studying this, I mentioned, maybe I haven't mentioned it, but I will mention it now. We talked about shortages of nickel and cobalt and lithium. Lithium, we're going to be safe. Nickel and cobalt, nickel is down here, cobalt's way down here. And so the question is, well, what about copper? Copper's here. Copper's 2 orders of magnitude lower than steel. But as you begin to electrify, there's growing concern that we will eventually run into a copper shortage. Maybe not 50 years, more likely 100 years, but hey, that's copper. And so one of the things that I've been going around giving talks over the last half dozen years is, given this not imminent tomorrow, you don't worry about copper futures, worry about 50 years from today, we may have a shortage of copper as we electrify. Tons of carbon. We know that carbon in the form of graphene, carbon in the form of nanotubes, and in terms of conductivity per unit weight is comparable and slightly better than copper. And so if you can turn copper into, sorry, not copper, carbon in the form of, let's say, carbon black, which will be abundant because you can take methane, you can turn to hydrogen, and you get carbon black. What is carbon black used for? It's used to make tires, used to make India ink. If you do this at scale, you've saturated the carbon black market. So the first people can have a market, but afterwards, gone. If you can turn carbon black into a conductor, you have a big market. So you young people think about that, and you could become rich. And so let's talk about batteries. It depends on where you live. In California, it's estimated we would need a significant amount of batteries, and in the United States. But we have a tremendous solar, wind, as well as fossil fuel and hydro. Taiwan doesn't. And so you will need some standby turn-on power. This comes in a couple of forms. Mostly it comes in the form of coal, natural gas, and if you use that, you have to capture the carbon dioxide and sequester it. But remember, it's only a partial solution because there's still greenhouse gas emissions in capturing and sequestering carbon dioxide. And then there's nuclear fission or nuclear fusion. So if I look at the energy resources in Taiwan, and how do I know this? Well, I don't live here, so I just asked ChatGPT. And in 2023, we get 6 or 7% of the total electricity used, solar, 3 or 4% is wind. If you want to expand wind, the geography is not so good. There's lots of mountains and trees and stuff, and it's not like the United States with plenty of land. So if you want to develop wind, you have to go offshore. There's some shallow offshore wind, which could be adaptable, but it's more expensive. But optimistically, you could get to 30%. Very unlikely to get to 50%. And so the rest of this energy has to come from coal, natural gas, or fission. Okay, so now the world is waking up. There's a lot of people who don't like nuclear power in terms of fission, but this is changing around the world. China is now building 24 new fission reactors. I was asked yesterday, why is China building so many fission reactors? And I said, well, they're very concerned about climate change. They're the biggest installers of solar and wind in the world, in their country. They want to develop all the technologies that will be useful in this transition into a lower carbon future, and they think fission is part of it. So they want to own that technology. In the United States, most of the United States was against fission 20 years ago. But remarkably, it's changing. In 2023, 3/4 of the adults say fission is okay, because they weren't asked the question, do you like fission? They were asked the question, which would you like? Coal, gas, or fission? Different question. Okay, so let me ask the people here, what would you like? Coal, gas, or fission? I'm going to make it a little bit more refined. How many people think fission, nuclear power, compared to burning coal or natural gas, which is more dangerous? How many think fission is more dangerous than natural gas? Raise your hand. Couple. How many think burning natural gas? Coal is really dangerous, so I'm going to assume that you guys are smart enough to realize, leave coal alone. So we're talking about natural gas. And so how many think fission is safer than natural gas? Raise your hand. Okay, most people aren't voting. Maybe a little bit more. Okay, so here's some data. Brown coal is the worst in terms of deaths per unit of electricity produced, followed by coal, followed by oil, followed by biomass. Where's nuclear? Nuclear is down here. Why is burning things so dangerous? Because when you burn things, you make particulate matter. And it's hard to filter out the smallest particulate matter. It's called PM 2.5. It's smaller than 2.5 microns. The trouble with this, bigger particles get caught by filters in your nose and other things. But the PM2.5 goes deep, deep into your lungs and actually passes through the alveoli into your bloodstream. And the incidence of cancer, if you have only 5 micrograms per cubic meter, you've increased the probability of getting lung cancer by something like 40%. 5 micrograms is 10 micrograms is considered clean air. So because of that, the World Health Organization is trying to evaluate what do we do now, because if we say 5 micrograms is what it is, then it makes the costs prohibitively high. Okay, China is like 70 micrograms in Beijing. Okay, India's 200. And so people are dying in heavily polluted areas, and nuclear doesn't have that. What does nuclear have? Well, there are people who mine uranium and they're slightly radioactive, so maybe a higher incidence of cancer. You have Chernobyl, which killed a lot of people. You have Fukushima, that did not kill people immediately from radiation exposure, but it's estimated, given the amount of radiation, given the exposures people have measured, maybe 200 more premature deaths from Fukushima. Not 20,000. 200. Why I say 20,000? Because that's how many people drowned. But what got the headlines is not the 20,000 people who drowned. It was the increase in likelihood of cancer. So one has to have a perspective on this. Nuclear is 100 times safer than burning wood pellets in a power plant. Don't burn wood in your home. It probably is illegal now. And certainly don't burn it in a home for cooking, because it's that particulate matter and the carbon monoxide that kills you. Okay, so nuclear statistically is pretty safe. It's a little bit safer than wind because people fall off wind towers. What people also don't realize that you eat about 1/3 of your natural exposure to radiation in the form of potatoes and carrots and bananas. And because of that, some of us have developed a tongue-in-cheek unit of radioactivity. It's called a BED, banana equivalent dose. You eat 1 banana, you get a certain amount of radiation. It goes into your body, and that ionizing radiation is irradiating your DNA. In Asia, if you eat a cup of bok choy, it's 1 banana worth of radiation. Does that mean you shouldn't eat bok choy or bananas? No. In fact, these are lists of other foods that you might eat. The health authorities in the United States say don't listen to these guys. Eat as much as you like, eat as many greens as you should. It's good for you, and it will not give you any higher incidence of cancer that we can measure. Okay, so it's fine, because background doses of radiation over factors of 4 or 5, depending on diet, where you live, how radioactive the rocks are. If you like granite kitchen tables, you have to know that granite is radioactive too. This is not a health threat. Okay. What is another problem with nuclear? Well, in the last couple of decades, we forgot how to build nuclear reactors on budget, on time. But in actual fact, we forgot how to build virtually all big projects on budget, on time. And if you look at big projects like the Three Gorges Dam, the big dig is a Boston tunnel system, modernization of that, and you see the price overruns, 2.6 to 22 billion. Panama Canal expansion, 1.16 to 3 billion. Three Gorges Dam, usually China can make things on budget, on time, but look at that. And so 92% of all these multi-billion-dollar budget projects were over budget. And most of the reason was some bureaucrat decided, oh, the bidding price was too high, I want a lower price. So they got a lower price. But the real price is what they got. They got a lower bid. And so that is an issue. There's another issue. After 3 Mile Island, additional regulatory requirements shot up the cost of nuclear power, but it's not mostly the regulatory requirements. It was mostly the people who did not like nuclear. And the demonstrations shot up the cost because it delayed the project. People who don't like hydroelectric dams. So that delays projects. Anytime you delay a project for a couple of years, you go up in cost by a lot. And so the oppositional politics, anything that people don't like, in the United States, you'll find people don't like anything, or some people don't like whatever it is anyway. And so this is an issue. Now, there's a new kid on the block, and I know Taiwan is going through this big debate as to whether you want to keep the last nuclear reactors going, or even some people say, well, you know, hey, we can get 30% renewables, and the rest is going to be natural gas, and LNG costs a lot of money. And so what do you do? And the new kid on the block is there are new types of reactors. They're called small modular reactors. The new scale one on the left is a shrunken down version, re-engineered version of a pressurized water reactor, the kind made by Westinghouse. The more exciting technologies are things like X-Energy, for example, and other companies are saying we put the nuclear fuel in a little pellet, it's about this big, surrounded by very durable ceramics, multiple layers of ceramics. And so you put the pellets together, you create the heat that creates the nuclear power, and when the fuel is burned up to where you can't extract usefully any more fuel, you take the pellets and you bury them. The pellets themselves are the containment. And so if the pellets don't leak, you don't get leakage into the water supply systems and things like that. So this is inherently safe because of the design of the fuel. So this is causing a lot of excitement, not only in the United States, but around the world. The issue is these reactors will be walk-away safe. What does walk-away safe mean? Walk-away safe means I've lost interest. I put my 3-year-old in charge. No, you don't want to put your 3-year-old in charge of anything. You lose control, access to electricity, water, something like that. And what will happen? Can it ever melt down and contaminate? The answer is no. Well, ever is too strong. So let's just say you want the probability to be less than if you fly in an airplane and you get killed in a crash. I think if you can achieve that safety record, it should be good enough. But in any case, this is a very real possibility. Okay, let's talk about other things. The demand of electricity is going up. We talked about electric vehicles, you know about that. And you probably heard that hydrogen production might use electricity. Data centers turn out to be a very big deal. In this article written in 2015, green are data centers, blue are networks, wireless communications. This red is the production of the cellular communications equipment, and the yellow is televisions, computers, mobile phones. But the big thing is over here, this green, because these data centers are now beginning to be built for artificial intelligence, machine learning purposes. They're also used to mine Bitcoin and other cryptocurrency, roughly half. And so this is really increasing. By 2030, it's projected that 20% of the electricity in the United States will be in data centers and wireless communication. If you go on further, I've seen estimates as high as 30 or 40% of all electricity, including EVs, will be data centers. And because of that, the people who run these data centers are looking to nuclear. Microsoft has just signed a contract. They're going to revive one of the reactors at 3 Mile Island that was turned off, not because it melted. One of them did melt, and so it's damaged. It can't be used. 2 of them are being used, and Microsoft is going to invest over $1 billion to recommission the 3rd one, and they'll buy all the electricity for 1 data center, about 1 gigawatt. These small modular reactors are being looked at, and contracts are being signed by Amazon, Meta, Google, because they think, and you can put a lot of data centers around. You know, at dinner we were discussing this in Taiwan. The small modular reactors are nice. Instead of one humongous reactor or a couple of humongous reactors, you got to put it somewhere. You say, okay, you have little geographic areas in Taiwan, you want electricity. You decide whether you want a carbon capture and natural gas or a nuclear reactor, and it might change the dial. But the most important thing is these things are going to be much, much safer. Spent fuel. I'm an advisory board of a company that's using borehole technology, oil drilling technology. This big around, you go down and you dump the nuclear waste down a kilometer, and you can have access to geological sites you couldn't have access to by building tunnels. And so this is causing some excitement. There are several countries around the world, including the United States, a couple in Scandinavia and in Europe, that are now contracting to test this way of storing spent fuel. And so the spent fuel problem could easily have a technical solution for even places like Taiwan. Now, the data centers themselves are using, we're talking about hundreds of megawatts to a gigawatt per data center. But let's compare to another computer, for example, the brain of this young lady. Instead of using 1 trillion parameters to identify tell the difference between a cat and a dog, she figured out what a cat was with much less data mining. She's what the future vice president says is a childless cat lady. But anyway, she uses 70 watts. 70 watts to learn multiple languages if her parents speak different languages. 70 watts tells you the difference in cats and dogs, and that food falls down, not up, and far less data. Really, millions of times less data than these large artificial intelligence machines. And so this just tells us we haven't figured out the right architecture yet. And so again, this is a little bit of excitement. I could spend a whole lecture on people talking about some new ways, new architectures that begin to try to mimic the human brain and learning. Okay, we need a fourth agricultural revolution. You might ask, what about fourth? What are the other ones? What were the first agricultural revolutions? A little bit of history. This is present day, going back 400,000 years. This is the temperature record from ice cores in Greenland. Temperature record in Greenland, just to let you know, is you're measuring the abundance of oxygen 18, oxygen 16, that the ratio is temperature dependent, and it's been well calibrated. Present day, ice age, warm, ice age, warm, ice age. This was about 1.5 degrees higher than we are today. Sea level was 6 to 9 meters higher. That's not a climate prediction, that's history. If you go back further, if you're 3 degrees higher, you're 100 meters higher. History, okay? So this is present time. Let's explain present time. In present time, let me go further. If you expand that, you find that the climate, instead of yo-yoing up and down in temperature, became stable. It became stable at about 10,000 BC. That's 1,200,000 years ago. And what happened 12,000 years ago is agriculture started. It not only started in the Fertile Crescent in the Middle East, it actually started in North and South China, New Guinea, Ethiopia, and the Americas. And it wasn't a transfer of technology. It was the climate became stable, and because it became stable, people could grow food. And that led to a stable society. It led to wealth, so you can have kings and physicists and other parasites? No. You could have civilizations and social order and things like that. And it's remarkable because Homo sapiens started around here. The size of the brain was about as big here as it was here, but no agriculture until here. So it was the climate stability that gave us this. Our climate instability will do the opposite, no matter how big our brain is. And so second agricultural revolution was discussed by Robert Fogel, Bob Fogel, a friend of mine, and he said, you look at all the civilization, beginning of the first agricultural revolution, invention of the plow, mathematics, metallurgy, all this other stuff. This is, by the way, population on the y-axis. And then he puts at this cusp right here, the second agricultural revolution, okay? And then it zoomed. You needed excess capacity of food production to create more wealth that led to higher civilization. And so, in the first agricultural revolution, we domesticated wheat, rice, cattle, chickens. We invented yeast for bread. They had the first irrigation, and we learned how to make alcohol. Very important. The second agricultural revolution was not an invention, it was policy. It started in England. People were allowed to put a fence on their land so that only they could use it. And because only they could use it, it wasn't overgrazed. They could raise crops. They increased the transportation system, and they had monetary things so you can use money to buy and sell food. And so that policy thing actually spread to Europe as the second agricultural revolution, and then more wealth. Third agricultural revolution, much more recent. It was the invention of fertilizer made from nitrogen, taken ultimately from the air, received 2 Nobel Prizes for the so-called Haber-Bosch process. Why 2? Because it was that important. In fact, there were 2.5. They gave a third Nobel Prize. More recently, they said at last we began to understand the real chemistry and physics of the Haber-Bosch process. That's part of the third agricultural revolution. Another part was the crossbreeding of plants led by Norman Borlaug and others, and he made a dwarf strain of wheat that had much, much higher output, could take a lot of fertilizer and water and higher yield per acre. Let me skip that and just go to this. 1961 to 2021, the land used to grow cereals like rice, wheat, oats, corn, constant. Here's the population. It went up 250%. Same amount of land, all over the world. And so this was a remarkable thing, and it meant we can feed a world of 8 billion people. But it has some downsides. There's lots of greenhouse gas emissions from the agriculture, methane from, let's say, cattle, and mostly in belching. If you feel guilty about eating meat, you can feel happier about eating pork. It has 8 times less greenhouse gas emission than beef. We're trying to modify the beef by putting microbes that don't make the cows burp as much. It's kind of finishing school for cattle. The microbes are parasites. They steal the food from the cattle and they make methane. So that's beef. Here's the CO2 emissions. If beef and dairy cows were a country, they would have more greenhouse gas emissions than any other country except China. So it's significant. This is part of geoengineering. I have to say, if you take the mass of human beings and the animals we eat on one side of the scale, and all the other mammals on the other side of the scale, like lions and tigers and bears and mice and squirrels, okay? Which weighs more? Well, we do. We are 95% of animal mass. 95%. We've geoengineered the world. Here's the problem. When you use fertilizer, which is absolutely necessary, it comes out of the ground in terms of N2O. As there's wastewater treatment, there are other things. And so this N2O is 300 times worse than carbon dioxide and lasts 100 years. And as the world grows richer, it's going to use even more fertilizer. And N2O is about 7% of greenhouse gas emissions. As we decrease CO2 and methane, this will become a significant part of all greenhouse gas emissions. And we cannot not use fertilizer. Otherwise, we can't feed 8 billion going to 10 or 11 billion. And so there may be a technical solution, and the solution is that you make microbes, you genetically alter the microbes using something called synthetic biology, These microbes live in the interface between the roots and the soil. They grab nitrogen, naturally occurring nitrogen that comes in from the atmosphere, and they feed the plant. And the plant keeps the microbes happy. Pivot Bio is a company in the Bay Area that has developed this. You plant these microbes with the corn, and you use half the fertilizer, but you want to get rid of all the fertilizer. You want it true for all the grains. You want microbes that where you flood grow rice, that you don't have methane emissions from rice. That's also microbes. And so the opportunity and the challenge is to use what we know in biology, in synthetic biology, to get rid of the greenhouse gas emissions, both methane and nitrous oxide from food production. All right, we're likely to go over 500 parts per million, as likely as I will go likely over time. 3 minutes over. And so what do we do about this? We're emitting 52 gigatons, and it's a huge amount of carbon dioxide. The cost of capturing carbon dioxide is very expensive. So when people talk about it, it's kind of an academic talk. This is a carbon dioxide capture plant that was funded when I was Secretary of Energy. It was the first one on budget, on time. It cost $1 billion for capturing a quarter of the carbon dioxide from a coal plant. That's the size of a big US-sized pickup truck. And so this is a big thing, and it uses 30% more of the energy of the coal plant to capture and release the carbon dioxide. And so this is not ready for deployment. There are other ways of doing this, but as a physicist, you ask, how much energy do you really need to capture and release the carbon dioxide? It's given by entropy. Entropy means you go from low concentration to high concentration. Increasing entropy goes from high to low. You go to low to high. Second law of thermodynamics says you have to pay a price. And the price is nothing. It's to capture from 400 parts per million to 1 atmosphere, it's only 20 kilojoules per mole. What do we use now? About 400, 200 kilojoules per mole. And so why are we doing that? It's because we form chemical bonds of carbon dioxide with amine, and it costs energy to break that chemical bond. So we have figured out a way, we is me and a postdoc of mine, 𝐷𝐸𝐿, have figured out a way to capture carbon dioxide without forming chemical bonds. And it looks pretty good. It begins by using a very alkaline solution, high pH solution. We know that carbon dioxide goes into forms of other carbon, bicarbonates and carbonates. If you have a pH of 11 and you swing the pH from 11 to, let's say, 5 or 6, the pH changes by 3 times 10 to the 4. So if you expose carbon dioxide to water at very high pH, it absorbs carbon dioxide like a sponge. And so all you have to do is swing the pH to 5, and it gives it up. This has been noticed by many people long before us, a decade before at least. But swinging the pH by increasing the proton concentration. Alkaline means low, high pH, low protons. You go to more acidic, more protons. You go from low to high concentration. Same law of thermodynamics. There is a minimum energy. And it costs, for a pH swing of 7.6, it's about half an electron volt per molecule to release. And that's a big energy penalty. It's a factor of 2 less than before, but it's still a big deal. And so what we did is we took a molecule, we put an amine on the molecule, and we said, okay, let's do this, thinking that we can break the amine bond, but only the amine bond, so we leave the other stuff alone. It could be more efficient. And it captured and released CO2, but there was no CO2 on the amine. We know this from mass spec. Got rid of the amine, put an OH instead, captured as well. That's interesting. What's going on? Well, we said, well, what's the pH doing? The pH, if we oxidize this molecule, it's a stable oxidized state. That's the red or orange, and that's the pH. So it tracks. So we're changing the pH, but we're using 20 times less energy than the absolute thermodynamic minimum of changing the pH. Okay, so here's the thing. You cannot violate the second law of thermodynamics. Okay? It's really against the law. So what are we doing? Let me just say that you can put CO2 in the thing and you oxidize this thing and up pops CO2, so we know this all works. I talked about the minimum law of thermodynamics. And so how can you change the pH without changing the proton concentration? Does anyone know? Okay, so we didn't know either. So we looked up what pH meant. It's a start. You can even look at ChatGPT. And the pH is minus the logarithm of the hydrogen concentration times a fudge factor, called the activity factor. And it was invented 100 years ago that says if you have a high concentration of whatever chemical species, you could have collective effects that make it effectively a higher concentration or effectively a lower concentration. And so what we found through experiments and molecular dynamics and just scratching our heads and thinking was, suppose here's our molecule, it's oxidized, it's in a charged state, the charge is on this blue thing, it's a nitrogen atom. And you see this water molecule, this is oxygen, 2 hydrogens, it's slightly negative here, slightly positive here, so this is polarized. So it's polarizing the water molecules around it. You can put in a mole of this stuff, so it's a lot of polarized molecules. Suppose there's a chemical reaction that takes a proton, combines it with a bicarbonate to form carbonic acid, neutral carbonic acid, that then combines with OH, it's very basic, and forms CO2, and the CO2 comes out. So you've used up the proton. So what this thing does is these polarized protons then, in this water molecule, then says, you used up a proton. I can donate a proton from these polarized molecules much more easily than from the normal water molecules. So it's a replacement mechanism. Use a proton, I'll give you another proton, but I'm not going to give you more protons now because then I have to pay a thermodynamic cost. So I just keep it the same. And meanwhile, CO2 goes out of solution. And another way, so we had an inkling from molecular dynamics simulations, but then you do an experiment, you say, okay, you put these charged molecules in with a lot of water, and you say, I'm going to throw in KOH. You throw in KOH, you put in OH, it's going to make it more basic. And there's a linear relationship in the log of pH and the log of this, and said, nope, doesn't work. The pH is buffered, it stays relatively constant until you've thrown in so many OHs that those polarized water molecules are all used up. You get one polarized water molecule per charged molecule. And at that point, it can no longer maintain the pH as acidic, and it gives up. So it's a buffer. So it's a new kind of chemistry. You're replacing protons as they get used up, but you have a supply of protons. Okay? And therefore, you don't pay the energy penalty. And so this is how it works. Now we have to convince the rest of the world, especially the electrochemists who missed it. We talked to inadvertently talked to one who said, this is great. He's an electrochemist at Harvard. And the one who first reviewed the submission said, no, this is all wrong. I don't see how it works and everything. And within a month, he'll figure out, oops, he missed it. But anyway, he got angry. This is what happens when you discover something and you don't know any electrochemistry. People get mad at you, but that's okay. We're right, and it works. And so this is very exciting. This is probably my most important scientific work in my career. Better than laser cooling trapping, better than animate ferrometry, better than single molecule biology and polymer physics. It's new chemistry, and it will have, I think, profound impact on the world. So I'm kind of an Kevin, much more important than battery stuff. But nevertheless, I'm still wanting to develop other ways of sequestering CO2. And so photosynthesis is great, but most of the CO2 gets cycled and turned back into gaseous CO2. But look, crops we plant, 10 to 18 billion tons of CO2 a year of the crops we plant. And so that's why people are talking about reforestation. You grow trees, you sequester the carbon in the trees. But I have a new method of sequestering carbon using photosynthesis, and it's based on a new material, not based on electrochemistry. The material is called wood. Here's how it works. You build a wooden building instead of steel and concrete. The wood is coming from cultivated forests, not from old growth forests, so it's wood laminates. It's a little more expensive than steel and concrete at the moment, but wood lasts a long time. Old London has 1,000-year-old buildings. Forbidden City is 600 years old. If we provide incentives to build wooden buildings, this 20-story tall building, no steel and concrete, and you keep the building going for 500 years, you sequester carbon, it's better than a forest. And it doesn't saturate because you build more wood buildings. And so that's the idea. It needs a little policy nudge to get the price down so wood composites become very competitive with steel and concrete. Transition. US transition from wood to coal, and then coal to natural gas and petroleum, natural gas to petroleum, hydronuclear, and other renewables. Look at the transition from coal to natural gas and petroleum, about 60 years. That's great. So is that going to be the history of the world? Nope. The rest of the world, anytime there's a new energy source, you put in another energy source. Okay? So we're not transitioning so far. And so this is what we're doing. We're on a collision path to 3 degrees, so I want to leave you with this image. It's the Titanic. If those of you who saw the movie, there are these 2 young people in the crow's nest up here, and they see, off in the distance, they see it's an iceberg. And so they go, iceberg, iceberg ahead. Very dramatic music, and they go down, they reverse the engines, and the kids up in the thing said, turn, why are you bloody turning? You gotta turn. But they didn't turn in time. And why? Because it takes a long time, at least 60 years to turn this ship. We're not going to be carbon neutral by 2050. Impossible. If we're lucky, we'll be carbon neutral mostly by 2075, 2080, because it's going to take a long time. But we better start turning now. Thank you.
Thank you very much, Steve, for a very insightful and stimulating talk, and many of the project, many of the directions that Professor Chu talked about are in fact what we are working on. For many of you works sitting in this room know that that's the direction that we're pushing forward. So now we have about 10 minutes for questions. Yeah.
Thank you for very inspiring talk. I'd like to sort of bring up a cautious reading of the data you show about the death rate per unit electricity. Okay, just let's do a simple mathematics.
Okay.
Okay, comparing the coal burning power plant and the nuclear power plant, the damage caused by the coal burning power plant is non-localized. It's open system.
Correct.
Right? But the nuclear power plant is closed system.
Right.
So let's do a simple mathematics. I don't know the actual number, maybe you have. Assuming 1 out of the 1,000 nuclear power plant giving the trouble. Okay, the average number must be divided by a big number of the reactor that is not causing any problem. But let's say if it's only 1 out of 1,000, then the number is underestimated by
Okay.
3 orders of magnitude.
Okay. So.
Right?
Okay.
So that would be something we have to read it with
Okay.
cautious.
Okay. So
cautious
So
attitude to
okay.
say-
So your point is that there are a certain number of nuclear power plants. In the United States, there are about 100. I'm going to guess in the world there may be 500, maybe, I don't really know. We've had 2 accidents that have caused deaths. Chernobyl, thousands of deaths. Fukushima, no direct deaths from radiation. Maybe 200 deaths estimated for premature deaths from cancer. So we count premature deaths from cancer as legitimate. And so it's 1 accident every roughly 20 years, 25 years. Okay, and that's what you have to compare. And it's localized. In Fukushima, the radioactive cloud was just trapped in a little valley going up to the northwest of Fukushima. There was some concern about fish being contaminated, but lots of studies. The IAEA did a very extensive study about the contamination of fish there, and they came to the conclusion, you should read this report, that if you eat 3 or 4 fish meals a day, there's a little border of 1 or 2 kilometers outside Fukushima, don't fish there. We said, okay, just take out just at the border, how many deaths would there be? Way less than the 200. Because it got diluted very quickly. And so, whereas the deaths from the non-localized deaths, it's actually surprisingly localized, the deaths from a coal plant, because most of this particulate matter is kind of downwind from the coal plant. The carbon dioxide gets spread out over the world. And so the death estimate from PM 2.5 especially, there's also SOx, NOx, mercury, that stuff, is just statistical epidemiology. So you have to look at the assumptions you were making about that. So you have a couple thousand from Chernobyl, maybe 5,000, I don't really know. It could even be 10,000. 200 from Fukushima, 0 from 3 Mile Island. There was not enough radiation that leaked out. And so you have to aggregate the whole time the nuclear power plants were, and that's where the numbers came from. And so what I do is I encourage you yourself, because this should be dispassionate, apolitical. It's records. You can go out there and look, and try to look for yourself and see if what is true. Are these surveys true or not? By the way, there were other estimates made by others. And it does vary. There's factors of 2 or 3 in the wind. The numbers I were giving you are somewhere in the middle. 2 or 3 meaning instead of being 1,000 times more deadly, it could be 300 times, or it could be 3,000. So I would just say, hey, let's split the difference. We'll just take 1,000 times. And so that is true. Now, it's hard to estimate deaths from anxiety. But if I was asked my Secretary of Energy, would you live downwind from a nuclear power plant? And I said, I wouldn't mind, but I certainly don't want to live downwind from a coal plant or a natural gas plant, because that really goes over. And even the mercury, which most countries don't regulate, we know causes real developmental damage among young people. And so I encourage you to look for yourself, okay? And you don't have to believe me. Don't believe me. Go yourself. But I did look into it a lot over the last couple of decades.
Yes, please.
If ocean is such a good heat sink, is it possible just make conduction to the deep sea to lower the temperature?
Well, that happens automatically.
But then increase the conduction even more. Right?
Yes. Yes, but but in the end, you're still going to look. Let's talk about heat in from the sun. The heat in from the sun is relatively constant. It goes through a solar cycle of 11 years, so it goes up and down. But averaged over many decades, it's pretty flat. Heat out less because of the greenhouse gas effect. So the heat goes somewhere. We know this because we have buoys. We have thousands of them. called Argo floats. Every 1 degree in the ocean, they go to the surface, they go 2 kilometers, the next generation down to 4 kilometers. They measure salinity and temperature. And the salinity is important because it also tells you density. And so we, for the first time over 15 years ago, we now actually have measurements of what the ocean currents are doing and what the temperature is doing. And then we said, oh my gosh, it's all going in the ocean, which is good. So it's keeping it cool. Now, if you made it really fast, so we don't go up now, after you warmed up the ocean, then you go up much more quickly. So unless you get rid of the greenhouse gas effect, you know, you can delay the price for, let's say, in your lifetime, but your children and grandchildren pay a bigger price. Okay, so the solution is you've got to stop the greenhouse gas effect or slow down the amount of radiation hitting the Earth. And this is that geoengineering of particulate matter and things like that. We may end up doing something like that if we get into this very bad situation of 3 or 4 degrees. But you really want to get rid of, and geoengineering doesn't really get rid of that stuff and the acidification of the ocean and all these other things that are happening. By the way, I want to give you assurance. People say, oh, the acidification, oh, so all the marine life is going to die because the little phytoplankton are going to die. And so I teach a course in physics of climate change and energy. I look back at the history. We were much warmer before, and at that time the CO2 was much higher and the ocean was more acidic. The species, the same species, were alive. But so the question is, so will they get wiped out? Well, we don't know because it was a geological time to go from one to the other. But the small microbes are fast doubling times. Could they evolve fast enough? We don't know. So it's an open question. So, but in terms of the temperature, no. You got to make the sun dimmer, or you have a few percent less sunlight hitting the Earth.
So did you ever do a back-envelope calculation? If increase 2%, like from 90% to 92%, how much temperature will drop?
No. The excess energy is in the order of 2 or 3%. You probably know that. That's the imbalance, and it's all going to heat the ocean. So you can change things by just a few percent, and it has a profound impact on the climate of the Earth. But 5 degrees, unlike what the nominee for the new Secretary of Energy is, he thinks 5 degrees is no big deal. He's publicly said that, and I said, no, wait a minute, 5 degrees now and ice ages is 5 degrees. Here, 5 degrees warmer, very different world. But he thinks it's no big deal because temperature in Chicago changes by 15 degrees in one day.
We need some gender balance.
Yeah, we need some affirmative action for men. Yeah?
For the speech, I would like to comment on the death rate of the coal and the nuclear, because I think that the resilience of a local area is different, such as the risk. If you want to compare the risk, you need to think about the small island like Taiwan or big country like USA or Japan. So the risk, we need to think about the resilience.
Yep, you're absolutely right. I mean, there are certain areas where actually life might improve. I mean, there's some people in Canada who think, hey, warmer weather, not so bad. And so it's, and actually some people say, well, look, if it gets too hot to grow grain in the United States, you just go to Canada. And they're unclear on the concept. The Earth is like this and the sun goes like this. It doesn't go like this, less sun. So there's true that some people will benefit from warmer, but on balance, many people will not. But my worry is the collapse of local agriculture, and hence the collapse of local social order and refugees. You don't need refugees from all places. You just need refugees where the social order has collapsed. And that becomes very bad. And so I think you can't say, well, life will get better for some. It's more, we're running risk of social order collapse.
Okay, let's thank Dr. Chu again. And before we leave, we want to take a group photo. So stay put, stay where you are, and we take a picture. Let's thank Dr. Chu again.